All right, so we have a piece of steel. Let's just, I suppose, treat it as a wire, and it has an initial length of 10 centimeters, and it has a mass of 40 grams. And it's subject to a heater that is supplying heat at, both ends, I suppose, or, the problem doesn't say, but the power of this heater is 2,000 watts. And the transfers heat for a time interval of 105 seconds. And so the steel then expands by an amount delta L. And we're told that the specific heat of steel, we'll just call that C because we don't need to distinguish between this and any other element, is 420 joules per kilogram per degree Celsius. And the coefficient of linear expansion is 12 times 10 to the negative sixth, basically degrees Celsius, or to the minus 1. And also, lastly, the Young's modulus for steel, we can write it's about 200 gigapascals. So, part A asks us how much heat is transferred to the steel. So the amount of heat, let's call it delta Q, is just going to be the power applied to the steel over this time interval. So 2,000 watts times 105 seconds is 2.1, let's write it this way, 210,000 joules, so kilojoules. So that's how much is transferred there. Simple enough. Part B, what is the temperature change of the steel here? So what we have is the same heat flow is going to be the mass of steel times the heat capacity times the temperature change. And so we can see, of course, delta T is just delta Q over MC when we convert everything to the appropriate units. So let's write this as 210,000 joules over our heat capacity, which is 420 joules per kilogram per degree C, times our mass, which is 40 grams. So we'll write this 0.04 kilograms. So if we plug in all of those numbers, we get a temperature change of 12,500, and the units will be, I guess, degrees Celsius. So extremely high temperature change. And then the part C asks us to find what's delta L. Well, delta L is going to be the initial length times 1 plus alpha times delta T. If we look at our equation for linear expansion, or sorry, there's no 1. This is just L times alpha times delta T. That's what I meant to write. And so let's see, make sure we got everything right. Yeah, so if we calculate this, we'll have 0.1 meters times 12 times 10 to the negative sixth per degree Celsius inverse times 12,500 degrees Celsius. So this gives us a total length change of about 0.015 meters, or 1.5 centimeters. And yeah, so then part D asks us what tensile strength would be necessary to produce the same amount of expansion. So what we'll have is like the equation that relates all this is like Young's modulus is equal to we'll call it tensile strength sigma times L over delta L, something like that. So our delta L, if we solve this equation for it, is going to be equal to basically sigma times L over Y. And sigma is our tensile strength. So, we're solving for the tensile strength. So if we can rearrange this even further, this delta L times Young's modulus over L is equal to sigma. And so if we plug in our numbers, this is 0.015 meters divided by 0.1 meters times 200 gigapascals. And this will give us our tensile strength in gigapascals. So this basically is 30 gigapascals, or 3 times 10 to the 10th pascals, or maybe newtons per square meter. Depends on what units you're comfortable with. But they ask for pascals, it looks like. So there you go.